Now this accelerator driven systems, or it is called accelerator driven subcritical reactor systems, they are of great importance to whole world in general and to India in particular. This system was discussed briefly in lecture number 9. Here I will give more details. Now if you take the use of, right now there are three main sources of energy. One is coal, other is oil, and third one is gas. These are the three resources, reserves known at this moment. And it is estimated that the coal will last only about 250 years, oil about 50 years, and gas about 65 to 70 years, in this range. That means we have to find a new source of energy, because when these all three sources they are finished, then there will be problems. So use of solar and wind is picking up right now, and of course nuclear power appears to be inevitable options as future energy source, because that will be a safe as well as cheaper than the other ones. Of course now solar energy's cost is coming down. However, in this case, disposal of nuclear waste in any reactor, these radioactive nuclei are formed, and they are called nuclear waste. One is plutonium, neptunium, americium, and curium. And that is an important issue in harnessing the energy from the critical reactor. They are more formed in the critical reactor. So if we can find a system where these nuclear waste nuclei are not formed, or they are made use of in some way or the other, then the system will be acceptable to everybody. Now in a conventional system, how it works, conventional reactor system, normally we use uranium-235 and a thermal neutron interacts with it, and that breaks into two nuclei plus few neutron because of fission process. And in this process, an energy of about 180 MeV to about 0.2 GeV is released, and that is what is used for generation of electricity. Now the problem comes here that uranium has several isotopes, and only one of them, for example, uranium-235 has only 0.7%, and which is fissile. So uranium-235 percent is only 0.7%, which and this uranium-35 is fissile. So that means this fission can take place only with the uranium-235, while if you take that uranium-238, which is 99.3% roughly, which is a fertile material and is not a fissile material, so it cannot be used for energy production in conventional reactors. So this basically becomes a waste actually. It has to be taken care of. Not only that, not only these ones, but even several minor actinides are produced, as I mentioned in this case, and that minor actinides are produced with heavier isotopes of uranium like 238 when neutrons are absorbed. Not only minor actinides but also fission products are produced. So some of them are listed here, and their half-lives are also mentioned, and you can see that it will take a lot of time for them to reduced to other two safe elements or other two safe isotopes. In the case of this reaction in fission, several fission products also are formed, and they are also radioactive, and they have to be taken care of. For example, some of them are mentioned here: strontium, cesium, iodine. So, in conventional nuclear reactor, taking care of nuclear waste, which consists of minor actinides and fission products, is a problem, and that is why not many people are happy about it. So, to solve this problem, in November 1993, Professor Carlo Rubbia, then Director General of CERN, Geneva, proposed a system which he called thermal neutron energy amplifier system based on thorium cycle. So far we were using uranium cycle. Now he is proposing thorium cycle, and why it is very important to us, that you will see in the next few slides. So he proposed that you can use thorium cycle for the energy production, and that is called ADS. Why it is very important to India? This can be seen here, that although we have not much of uranium, but we have highest amount of thorium available in India, and this is, you can see here, that India is having highest amount of thorium, and this is the latest report. This is in thousands of tons, so you can see almost like 1 million tons of that, and these are the references for them. So roughly almost like 16 to 17% of world's thorium is in India, and that's a very good quality. So if we can use thorium in our reactors, then it is estimated that our fuel problem will be solved almost for 500 to 600 years. So this is a very good, and I think India should really work on it. And that the system which proposed by Professor Carlo Rubbia is called accelerator-driven subcritical reactor system. Why it is important to have subcritical reactor? Because in conventional reactors producing power due to criticality, safety issues are involved. While if it is subcritical, then that problem will not come and it will be inherently safe. So what he proposed was that you have a subcritical reactor, and the extra neutrons which are required, they will be coming from outside, and they are generated by the accelerator system. So it's a new kind of fission reactor where nuclear power, let's say just for example 500 to 1000 megawatt electrical, can be generated in a neutron multiplying core, and K effective here is less than 1. So that means it is subcritical. So this, if K effective is less than 1, it is subcritical. If it is equal to 1, it is critical. It is critical. Here it is subcritical. And if it is more than 1, then it is supercritical. Now, this will be inherently safe if K effective is less than 1. K effective is shown here. That means the production of neutrons is less than the absorption plus leakage. So that means it will never become critical. Now, if it doesn't become critical, then power generation will not take place. So how to make it critical? That means you have to provide extra neutrons from outside, and that makes it critical. But now the control will become on the system which you are using from outside. and that is what is ADS. So the extra neutrons come from the accelerator part. So accelerator has to be driven by an external neutron source. This is very important, and that is what is done by the accelerator. So neutron source requirement for ADS is given here. So let us take 1 GeV, a proton beam, interact with the heavy nuclei, produces about 25 to 30 neutrons. Now it's not a fission reaction, it's a spallation reaction. So each proton will generate about 25 to 30. And why it has to be about 1 GeV, you will see in the next slide. So suppose for the sake of calculations, you take 10 milliampere beam current, or 10 milliampere 1 GeV becomes 10 megawatt. So that is a beam power. So this reaction can yield about 10 power 18 neutrons per second, because each proton is creating 25 to 30 neutrons. And this neutrons per second, you will see here, can generate the nuclear power of 500 to 1000 megawatt. So if you take fission energy liberated in a neutron multiplying core, K now is a subcritical core, then it is given by this formula. 180 MeV is the energy released in each fission reaction. So if you take K effective less than 1 but of the order of 0.95 to 0.98, then the thermal fission power in the range of this would require driving neutron source of that, and this is already there. You have seen it. It can be generated there. So that means with this 1 GeV proton beam of 10 milliampere, you can generate a nuclear power of about 1000 megawatt. From where that 25 to 30 neutrons per proton comes, it comes from here, based on the calculations as well as the experiment. So you can see this figure where the number of neutrons generated per proton in a normalized manner as a function of proton energy. You can see that around 1 GeV, this is 1 GeV, it saturates, and it is around 25 to 30 in that range. With other, this is on the lead target, but if you have other target, it can be slightly more or less. So you can see that on the average in a spallation process, when the 1 GeV proton beam interacts with a heavy target like lead or bismuth, then it will generate about 25 to 30 neutrons. Of course, having a full spectrum, so you have to moderate it. And if you have that, and these calculations were done at Fermilab, and I have taken from this figure from invited talk given by Chandrasekhar Mishra in the INPACT 2005. Now, in BRC also initiated this program. As I said that for India, it is absolutely of great importance to have an ADS program. And there, this is the accelerator. You can see here, it will go about 1 GeV, 30 milliampere. In that, proton beam will fall on a spallation target. For the region to take away the heat, it will be a liquid target. So this is a spallation target here, spallation target, and neutrons are produced, and it is surrounded by a core of thorium, and where the energy will be generated. So you can see that detailed studies have been done on high current accelerator, spallation target, and reactor system. And this program has started. So this accelerator will be developed at BRC in 3 phases. First one will be 20 MeV, low energy, high intensity proton accelerator. Second will be up to 200 MV, and at 200 MBV itself, you can have a demo ADS for physics studies. However, the power can be generated with the 1 GeV accelerator. So you can see that here, this even the smallest, this 20 MBV LiPA consists of several components, and I am happy to tell you that this is almost about to be commissioned. However, this development of 1 GeV 30 milliampere current accelerator is difficult because higher currents there will be lot of processes formed, like it's very difficult to contain that beam because of the space charge effect, repulsive space charge effects, and also because of beam halo problems. But those problems can be solved, and we are going ahead with that. Now you can see here that why 30, I am talking about 30 milliampere so far, and how that 30 milliampere comes, whether can be reduce that, because getting accelerators of that energy and the current are difficult. As of now, there is no high current accelerator operating in CW mode. So you can see if you calculate that thermal power generated using this current, you can see that for 1000 megawatt, you need about 30 milliampere if you have K effective of 0.95. However, if you have 0.98, then it reduces to about 10 milliampere current. Similarly, if you want to generate a power of 3000 megawatts thermal, then you need about 90 milliampere current with K effective of 0.95. But if you go to 0.98, then it reduces to about 30 milliampere current. So if you want to have this kind of power generation, which will be almost like about 1000 megawatt electrical, then you need at least 30 milliampere currents. So this comes from this formula for the thermal power, and the parameters which have been taken into account is that proton energy is 1 GeV, and number of newtons per proton is 25, and in fission we have taken that there will be each fission there will be 2.5 newtons produced, and we know that it is in the range of 2 to 3 newtons are produced per fission. To give you some numbers for reactors, that is converting into electrical power with 40% efficiency to 280 megawatt. Then how it will be useful using thorium? You can take that this consists of 3 subcomponents, which Carlo Ruvia gave. Actually, this is what he gave. You have an accelerator. Let's say it is about 1 GeV, 30 milliampere. Then it will be 30 milliampere, 1 GeV will be 30 megawatt. And the accelerator efficiency is about 50%, you can call it. So that means whatever power you are giving as an input, beam power will be about 50% of that. So you have an accelerator where you are feeding about 60 megawatt power, so you get 30 megawatt here, and this is what you want corresponding. So when this beam falls on a target, heavy target, and that gives you about 25 times gain roughly, because you are getting the. So if you have 30 megawatt and roughly 20 gain, you will get 600 megawatt of. That goes into the reactor, and which has a conversion factor of about 40% from thermal to electrical. So you get about 240 megawatt of electrical power. Out of that, 60 will go to the accelerator and this system, and 180 megawatt can go to grid. So you will see that initially you have to feed power from outside. Later on it becomes like a self-sufficient, independent system where power is generated and you can, whole system can be given power from this and extra power. For example, in this case about 180 megawatt power is available to the grid. So after some time it becomes a self-sustainable system. Now, also giving that what is the physics behind it, and if it is a subcritical system, you can see that the multiplication in the subcritical reactor is given by this, and the gain is given by this. This is for the subcritical system. And if you take a typical value of G naught, which is about in the range of 2.1 to 2.4, then you can see that K effective for 0.9, the gain will be 20, and for K effective 0.97, it will be 70, and so on. And then the K effective 0.997, which is close to the critical one and which we should avoid, then it will be 700. So that means even little bit of fluctuation in parameters can make it unsafe. So we should not use K effective of the order of 0.997. However, in this case which we are considering 1 GeV proton energy on the lead target, producing about 20 neutrons. You have seen it, 20 to 30 in that range. So typically, let's say 40% of these neutrons will create fission reaction, will have fission reaction. That means out of these 8 neutrons will generate fission, and each fission roughly gives about 0.2 GeV energy, 180 MeV. So roughly I am taking it about 0.2. Then it will generate 1.8 GeV. So that means we started with a 1 GeV proton, and it is giving energy of about 1.6 GeV. So we have to keep these parameters in mind. So with this order of magnitude calculation, so with K effective of 0.98, the multiplication becomes about 50 with all the parameters put in, and it produces about 80 GeV energy. So 1.6 into 50 becomes 80 GeV. So the energy multiplication effectively in a subcritical reactor system based on the 1 GeV accelerator becomes about 80. Now the beam power was 30 megawatt here, and it's multiplied by 80. So you can see that ADS power which is giving is about 2400 megawatts. So this is order of magnitude. This will exact calculations will involve a lot of other parameters. The biggest advantage of this is reduction in the minor actinides. And see, for example, for us it is very important to use thorium because it's a high abundance, and it is available in India in plenty. So therefore, and particularly it is 3 to 4 times abundant than the uranium. Right now, all our reactors are using uranium, and it is 3 to 4 times available. So that means we have a lot of better fuel performance characteristics which are listed here. You can see higher melting point, better thermal conductivity. This is very important parameter, and lower fission gas release. But most important is this parameter, which is comparison of minor actinides produced in this thorium uranium cycle is that is much less as compared to this cycle which is used in many reactors, and that is shown here in this slide, that the minor actinides production in thorium based cycle is, you can relative values you can see here. For example, in this one, you can see that neptunium 237, which was produced in uranium fuels, the uranium plutonium cycle, 4.6. Here it is only 0.06, is much less. Similarly, americium, which was 4 here, is -7, so it's almost like 0. And so therefore, and these were the minor actinides which were responsible for that: neptunium, americium, camerium. So these are and these are not even produced. So these are some of the very big advantage. That means your problem of waste management is automatically solved. So safety is taken care of. That means the ADS systems are inherently safe because the reactor is subcritical. Minor actinides are not produced, and India it is abundantly available. So this has tremendous advantage for all. So thank you very much for this. So this is the end of this course, and I wish you good luck.